Hey guys, today we're going to be going over the cube problem, or what I consider the cube problem. Basically, it's a problem that shows up on the SAT a lot, and that I personally probably teach or go through at least once or twice a day. So what they generally give you is some kind of cube or some kind of three-dimensional figure. It doesn't necessarily have to be a cube. It could be a rectangular prism or any kind of three-dimensional objects resembling a cube. But it is the same method regardless of the circumstance. So what they usually do is they ask you to find the distance from one edge, an opposite edge, all the way on the other side to another edge on the other side. So they are two opposing vertices. So I'll give you an example with the box. So let's say if you look at it, this cube, yeah, it's kind of weird to visualize on a two-dimensional surface, but if you look at the three-dimensional box I have here from FedEx, you can see that there's a vertex. So let's say we're looking at this vertex right here. This will be like the face of the cube. So it'll be from this point to this point right here. So I'll keep my fingers on it. You see how it's not exactly like a regular diagonal? Yeah. So it's a little more complicated than your regular, I'll take a square and let me just find a diagonal and I'll give you side, this is 2 and this is 2 maybe. Right? That would be nice and simple. Pythagorean theorem. A squared plus b squared equals c squared. Right? So that'd be 2 squared plus 2 squared, which would be c squared. 4 plus 4, c squared. 8 equals c squared. Now, square root, c equals square root of 8. So that's how you normally would get just a regular square problem finding the diagonal. But in this case, the diagonal is from one side to the other edge in a three-dimensional figure. So it's going all the way through, crossing through the inside of the cube. In this case it's a cube, it could be a rectangular prism. The only difference is the dimensions are different. In a cube, every side is the same. This is 2, 2, 2, 2, so on and so forth. In a rectangular prism, this could just be 3, but it doesn't matter, it's the same. Let's stick to a cube for this case. So, again, what they're asking for is the distance from this diagonal all the way to the outside. It's really important to understand that. It's cutting through, sorry for my non-straight line, but it comes all the way through the box. Again, back to this figure. From this edge to the other edge, it's opposite edges. You see that? It's really important to visualize it, otherwise you can't get a good grasp of what they're really asking. Now, what I tell with a lot of my students is whenever you see a geometry type problem, you always have to look for triangles. Look for small triangles which you can use to kind of envision the problem. And the same thing goes here. Your job is just to figure out which triangles you need to put where. So, if you look carefully, what triangles do you need? Well, you kind of know that this is 2, and you also know that this back side is also 2, and this thing going up is also 2, and so is this piece going all the way across, this is also 2, right, because it's a cube. If you check it out, you'll see that there kind of is a triangle already here. 1, 2, and 3. It's a triangle standing face up. If you look, there's a 90-degree angle, a three-dimensional triangle going straight up. It's literally standing straight up. And what we do know, what we don't know, what we need to know is the diagonal across. We don't know this side, but we do know the height here. So we kind of have this triangle. I'll just cut it out and show you what it actually kind of looks like without all these lines going through. I know this can get a little confusing. So imagine, isn't this kind of like the same type of triangle? It really is. We're asked to look for the diagonal. So we're looking for the hypotenuse here. Let's just label that x, right? And we know the backside here, the height here, is just 2. So if we know the backside, well, we need to know this side, right? In order to do our a squared plus b squared equals c squared, because remember, this is also a right angle. Almost every angle in here is a right angle, regardless of whether it's three-dimensional or not. So we're missing this piece, which I'll just label y for now. Okay? So now we have, again, 3 variables. We can't do much with it. You know, we're stuck with the y squared plus 2 squared equals x squared. We can't solve for this because we have 2 variables here, which means we possibly might need a third triangle. The third triangle, which I don't have enough colors for, I'll just make this in red. Is right here. It's really important. There's one triangle facing straight up and there's one triangle lying down. So I'll just draw another cutout. Now check it out. This side is 2. This side is also 2. But what happens here is the base here, which we labeled y, becomes the hypotenuse for the other triangle. Now we can solve for y. Simply I'll solve it right up here. Square root, square root. So now that we have y, which is the square root of 8, I'm going to erase this y and put in radical 8. Now look, I can erase this y, which is this triangle standing face up. So now we have 2 numbers, 1 variable. We can simply plug it in into our y. So what we're left with is square root of 8 squared plus 2 squared equals x squared. Whenever we have a square root and we're squaring it, the square root simply disappears. It's really important to understand and kind of visualize that you have 2 triangles here. You're trying to break down this really complex problem and create 2 separate triangles. One standing up, one lying down. And they both connect. You have to be able to see the connections here. In all types of geometry problems, in all types of these problems, it's really important to identify the problem and how to figure it out. Specifically, in most geometry problems, you can always create smaller figures. In this particular problem, all you have to do, all you have to know, is you have to look for 2 triangles which each have 2 separate Pythagorean theorems. In other words, you have two triangles, each with its own separate Pythagorean theorem problem. As long as you can understand that, the problem is simple. I'll give you guys the problem to do for yourself, and you guys can email me your answers, and I will separately email you the correct answer. This will not be a cube, this will be a rectangle. Not as though it makes much of a difference, but okay, find the distance from the red point. As you can see, it's the same type of problem we just went over. It's really important. Here's my email. Thanks for listening in, and I hope you enjoyed it.